the realization, commissioning, and other aspects that we do not often discuss when we speak of nearly zero energy buildings. So how everything started is actually, it's a long story, but the story started at around 2006. And at that time, some of my colleagues, including Pierre Heisenberg, who participated in the International Energy Annex 52. And in this annex, one of the questions that was raised is, what do we understand as a nearly zero energy buildings? Because we can speak of many different types of buildings that produce renewable energy, and whether it's electrical energy or heating energy, can we compare those? What do we understand by zero energy building? How close to zero we should be? Is this a building that produces an energy, or is it a building that doesn't use any energy? Is it a building that is producing an energy on the site, or we can produce by a windmill placed somewhere far away in the fields? And many of those questions that have been asked, they were asked within this Annex 52. And actually one of the outcomes of this work was to make a definition of the nearly zero energy buildings. As a result of this work, we actually started a collaboration within the Zero Emission Center in Norway. This center started in 2009, and it is still existing. It will be finished now in 2017. A corresponding center for zero energy buildings in Denmark started in 2009, and it's now closed. It's been closed since 2014. The difference between those two is actually that in the first one, the focus was set more on the zero emission center. So we speak of the emissions of the building. And over here, we have been focused more on the energy.
Excuse me, in this case, Norway, all the buildings are near zero.
No, not because all of the buildings are nearly zero, although this is the goal. But
if you use the electricity?
Sorry?
If you use electricity, the electricity in Norway, they don't have CO2, it's hydropower.
Yes, that's true. But the question is whether a building that has a huge energy spendings can be considered as a nearly zero energy building, although you compensate for all of the energy by renewable sources. And this is one of the discussions that has been held within the annex. And one of the conclusions was that actually a building that has a high energy spendings is not nearly zero energy building, although you can compensate for all of the energy that you spend. So the idea is what do we need to do if we want to get a nearly zero energy building? And of course, first of all, we would like to reduce the energy need in the building. And then, of course, in most of the cases, we will have some energy spendings, and those have to be compensated or produced by the renewable energy sources. And then how do we cover? How do we compensate? If our building uses, I don't know, 10 kilowatt of the electrical energy, can we compensate with the heating energy? Or how do we deal about that one? So actually we need to find a way how we account for the energy. Do we account by the primary energy? Do we account by the electrical energy? Or what is the other way of accounting for the energy? And finally, we also need to consider the embodied energy in the materials of the building that we use. How do we deal with this part of the building? So once we succeed in building these nearly zero energy buildings, what we do get, we actually get a building that has rather low energy use. We have the buildings that are consuming some of the energy, and in many cases that would also be a building that is actually producing the energy, what we call the prosuming buildings. We also get the buildings where expectedly the annual energy balance goes nearly to zero. And this annual energy balance, this is what is the outcome of Annex 52, that when we account for the zero energy buildings, we account on the yearly basis. We could have considered to account on the monthly basis or on a daily basis, but the conclusion was that that was the most appropriate way of accounting for the energy. And the final part here is that if our buildings are prosumers, they are producing the energy, then there are two possibilities. Either it's a building that is disconnected from the grid, or it is a building that is connected to the grid. If our building is connected to the grid, then it becomes a very important part of the overall energy system. And we cannot discuss a building as a standalone unit. In this case, we'll have to discuss or talk about the building as a part of a larger interface. So, the challenges that are related to the zero or nearly zero energy buildings is, of course, how do we determine the balance between the energy production and the energy savings? What do we, or how do we deal about that? How do we design the buildings that interact effectively with the energy system, or let's say the energy system and the network? And how do we design the buildings that can help our grid, or energy grid? But another aspect of all of this is actually designing our buildings to be energy flexible. So to say that our building can take some of the load from the grid, energy grid, and in this way release the certain possibilities as, for example, energy storage. To do that, we actually have some difficulties because we do not know some of the things, or maybe we are not as good as realizing those. First of all, we have a very big gap between the design energy use of the buildings and the realized one. By experience, we know that once we design a building, we calculate the energy use, but once we measure on the building, we find out that actually there is a gap. We can hardly measure the same energy use as we design. Another issue here is actually the indoor air quality and comfort, because we normally want to have very good indoor environment, but this is not always the case when we actually build our buildings. And of course, we would like to consider the functionality of our building, that it is living up to our expectations. So if we have to condense all of these discussions into some topics, one of those is the energy efficiency of the building compared to the renewable energy production. And this is a discussion that we have had just before, where we can on the x-axis can look at the delivered energy, or so to say the energy demand of the building, and on the y-axis is actually the production of the energy, or renewable energy on the building. So if what we have in this case, that if energy use in our building is rather high, that would also mean that the production of the energy should be correspondingly high. If we optimize our building and reduce the energy demand, then we will actually end up with rather small energy production. And of course, we do not do this one because it will be very difficult to compensate for the high energy demand, because it will be quite expensive. In some cases we do, of course, but that's not the optimal situation. The studies have shown that it makes sense to optimize the building to a certain level before we apply renewable sources. And for the example of Denmark, it is set by the governmental building regulations, where a certain line is drawn up and says that this will be the optimal life cycle cost or the investment cost for the consumers to go for this level. So we optimize to a certain level. We are not going all the way to the zero, because if you go all the way to the zero, it will be quite expensive. But if we stop at a certain reasonable point, then we can, with a reasonable cost, optimize our building and compensate for the energy use using the renewable energy sources. Again, looking at the example, the Danish example, we have a lot of different buildings coming from the 30s and 80s and 60s, and some calculations have shown that if we look at the single family houses from the 30s, we can expect 82% of energy savings if we renovate those buildings. And the value you can see is very similar for the buildings built in the other years. For example, the buildings from the 60s are also very poor, and they can be optimized and renovated. The y-axis is the price, how much you have to invest in order to optimize your building with regards to the energy. And x-axis is the energy used per square meter of the built area. So at the moment, a lot of buildings in Denmark, they're using at around 130 kilowatt hours per square meter. And for those cases, this is the orange line, we have a certain cost. If you look at the new built buildings, that will be the green line. And this green line, these are the new buildings. And there we start with the energy use at around 70 kilowatt hours per square meter. And we can see that the new buildings, they are rather cheap to build in order to achieve this low energy use. But if we follow the Danish regulations, the Danish regulations have been sharpened. So actually the expectations to the energy use in the buildings are very, very low, let's say. So actually we have to optimize our building even further. So right now we are at around 20 kilowatt hours per square meter per year. But this doesn't come without a cost. You can see those peaks that our buildings become very expensive to build. And this is because we have to use the mechanical ventilation system with the heat recovery, which has a certain investment cost. This is an example of the case study. This is a building that had to be built in the city where I live. And this was a building disconnected from the grid. Before they took the decision whether it has to be disconnected or connected to the grid, they have done the study, what will be the life cycle cost, whether we take different renewable sources and make a building fully autonomic, or whether we connect it to the grid. And here you can see the list of the different renewable sources that have been considered. There are the photovoltaic of different variations, and these are the connected on the site or produced on the site. And there are some renewable energy sources that are produced not on the site, and this is the off-site energy generation. And the results actually show that if the energy produced on the site, this is this part of the chart, and if the energy produced off the site, this is another part of the chart. Here we're looking at the life cycle cost for the different solutions, and you could say that yes, it looks very much alike actually, except for this micro CHP. What has to be said here? The chart can tell many things. But actually, if we produce the energy on the site, if we optimize our building with regards to the energy efficiency, then actually the life cycle cost will drop because we have to install the smaller systems, etc. However, on the off-site system, if we reduce or optimize our building and reduce the energy spendings, that actually the expenses will increase. So actually, depending on our building performance, this chart will change the shape.
Can you explain the different technology?
Those are over here.
Okay.
Those are and they're also on the USB. But if you're interested in more into that, because this is not me who did this work, there is a publication reference over here. It's published, so you can have a look at it. So again, speaking of the environmental impact of our buildings, we also can have a look at the different types of the buildings. We have the single-family houses and we have the offices. The idea is that we can look at the contribution of the different building constructions. For example, HVAC systems, windows, floors, etc. And here, if we look, then we look at the primary energy in total, and we have the single-family houses and we have the offices. The thing is that actually life cycle cost for in the calculations for the single family houses seems to be much higher than it is for the offices. And that is one of the calculations that has been made within this project. And we do have to consider the life cycle cost. But as I said, the nZEB, or Zero Energy Building Center, has not been focusing in Denmark so much on the emissions. Over here is the primary energy for the life cycle cost. Some of the other challenges that we are discussing is actually how the buildings they interact with the energy systems, if they are a part of the energy system. Some of the calculations that have been done in a building that is fully electrical, what we normally consider is that the building's annual cycle can look in this way, that we actually can produce quite a lot of energy in the summertime using the PVs, but actually the energy load in the summertime is reducing. But if you're looking at the photovoltaics on a daily basis, those are much better correlated to our daily cycle. Maybe not for the single family houses, but in generally for the grid, the highest energy demand happens during the daytime. Meanwhile, at the nighttime, we are not consuming. Yeah, the business hours, of course. But in a certain way, if we speak of the building that is fully electric, we can compensate both for heating and cooling using the electricity, if this has to be considered. This is one of the case houses which has been started by Carsten Wurst from Germany. But I think that this is the illustration that can apply for many places. And this is the case that I can speak more about. Yes, but this is the building, I don't know if you have seen it before, it's called House for Life, or in Denmark it's called Active House. The Active House is but it's in a way a research project which is a collaboration between the industry and the universities. And this building was built some years ago, and the idea with this building is that it has a lot of glazing area, of course. It has a lot of control systems involved, so the occupants, when they live in this building, they don't have to control a lot of things. So the shading is activated according to the indoor air temperature and according to the daylight level inside. It is highly controlled. And some people who has been there, they think it can be too much because you can feel how the internal shading moves, external shading moves. But this building has been measured in many ways. So what is the calculation for this building has been made, and we have a certain demand for the domestic hot water. We have the demand for space heating. There is an electricity for the operation of the house. Household electricity, this case is included, and we know about that one. There is a production of the electricity by the PVs. There is a solar thermal collector installed. And there is also the heat pump. So once the measurements have been done, we have the solar thermal collector, we have the photovoltaic system, and we have the ground source heat pump. The building is connected to the grid, and actually 2 out of 3, 2/3 parts of the energy has been, let's say, exchanged with the grid. These are the results of the measurements. Then there has been done some simulations to calculate what will happen if the solar collectors is replaced by the wind turbine. And in this case, the calculations have showed that the energy exchange with the grid dropped 2 times. And as a result, for this building, the conclusion was made that the solar cells are the better solution for this type of the building. But this is, of course, only one case. Some of the discussions that also has been made is with regards to the wind generation, because when we generate the electricity using the wind turbines, then of course we have very high fluctuations in the electricity generation. Meanwhile, having the solar collectors, we actually produce the energy in the business hours, where it is also the most requested, at least for the Danish network. So one of the things that is very difficult to discuss is that because we are used to look at our buildings as a singular part, and we are looking at the buildings as a standalone system, but if you are connecting them to the grid, then actually they become let's say, an active part of our network. And at least for Denmark, it's been one of the conclusions. I'm not researching in that area particularly, but we have a very good cooperation with another department that researches in the network of the energy system in Denmark. And what they have been looking at the building as a part of the, let's say, active system. So actually we can use a building as a battery in a way. So what we are looking at the building as an emitter or a collector. So actually using the building construction as a possibility to collect the energy. And this can be done by increasing the set point temperature inside the building at the moments when the energy is cheap, and reducing the set point temperature in the building when the energy is expensive. So actually when the energy is cheap, it's actually the situation when we have too much of energy in our network and that has to be spent. And this is what we do. We actually asking our building to use the energy at this moment to maintain the comfort conditions. Meanwhile, when we are not using the energy, we actually also saving some money. These are the results of the building simulation, and these are not the measurement results. We are looking at two types of the buildings. We are looking at the building that is built sometimes in 70s or 80s. This is a building that has a very poor building envelope, and it is, let's say, has a lot of cold bridges, etc. Another building case is the building that lives up to the passive house standard, a building that has very low heating demand, very good building envelope, and those two are considered. These are the results of the simulations. We are looking at the there is a red and blue and red. The blue one are the radiators and the red lines are the floor heating. So what happens if we, on the x-axis, if we activate our floor heating, our radiator for certain hours in order to store some energy inside of the building. So for this old building from 70s, if we activate the thermal mass for around 6 hours, we can see that actually the heating system can be switched off for maximum 5 hours. So actually we do not get much out of it. If we activate the thermal mass of our building for a longer time, then actually the performance of the, let's say, the time that we can switch off our system is not getting much longer. Very opposite results actually received for the very well insulated building. And it is, and those are the illustrations here, but we can talk on this example. The thing is that when the building is very well insulated, it is becoming much more autonomous, and by this means it might not be able to store a large amount of energy, but at the same time it is also not losing same amount of energy. This is the results of the simulations for the well insulated building according to the passive house standard. And I will tell you that over here we have at around 200, as far as I remember, 100 to 200 watt per square meter can be stored in our building. Although the building can store very little, the time that it has been storing the energy can go up to 24 hours. So to say, well-insulated buildings, they are much more autonomous, and by this means they could be used in a better way as an energy storage. If you look at the different scenarios for how we can use our energy system, we can look at the different solutions. What if we switch off our heating for 4 hours? What if we switch off our heating system for 6 hours? There could be defined some flexibility factors. But since it is very difficult for you to see the previous graphs, I'm not going to describe it any further because it doesn't really make sense. So I'll just drop over those. And if you're interested to know more about it, there is a reference, so you can read the publication on the science. These are the measurements that has been done in Denmark, and yes, on the x-axis we have the energy performance label, and on the y-axis we have the energy demand, and we have two columns. The light green color is the actual performance, and the dark green is the theoretical. How do we know the actual performance? First of all, these are the low energy buildings, or close to the low energy buildings, and those are the buildings of a poor performance, let's say so. And you can see that the lower energy, expected lower energy performance becomes, the higher, and yes, we have much higher energy spendings. And those are the results based on 230,000 of buildings in Denmark. As I said, I totally agree with you that very good indoor environment can also cost you quite a lot in terms of energy. But it can also be the situation where we have poor energy performance and poor indoor environment. This is, we totally agree about. This is only the energy. Besides, this is the energy, let's say, results based on the energy labeling in Denmark. So the positive side of this chart is that actually it's based on a huge amount of data. It's 230,000 buildings. That's on the positive side. On the negative side is that the data is achieved from the energy labeling. That means that the data is not very detailed. So there could be the deviation. But actually the issue of the actual performance compared to the calculated one is very well illustrated here. The one over here is the 2020 label. And if you compare with the passive house standard, it's a little bit different. There are different requirements. In Denmark, by 2020, we have maximum energy use is 20 kilowatt hours per square meter per year. For the dwellings, appliances are not included, also for the offices. But for the offices, the lighting is included. Yes. The reason is that the appliances in Denmark are not included is simply because this is a legislation and the government does not believe that they can require people of having a certain type of fridge or washing machine, etc. Yes, but in a way it illustrates the problem that actually we do not know much about our buildings. Because yes, and in the building regulations we do require the energy. We only advise what indoor environment we want to have. Save some money as well. Yes, yes. And the people that are living in the well-insulated, they are not taking care of it. Yes, but they're there. Yes, and then we can continue from here. So this is the building that you have just seen before. This is the building that has been standing empty for 2 years. And they were controlling and measuring how it's operating without interference of users. And then the family moved in, and the family lived in this house also for 2 years. So actually it has been documented, its performance for 4 years in total. And now the building is sold and it is not being measured. But what the outcomes of this study was that the energy used for heating was higher than it's been expected for the building. The electricity used for the heat pump was also higher than expected. And the electricity used for the control system in the building was also higher than expected. And this is actually the expense that's very often forgotten because those systems require quite a lot. On the other hand, in Denmark, we do include the domestic hot water in the energy requirements. And here, the use of the domestic hot water was much smaller. And this has something to do with our assumptions, our knowledge with regards to the domestic hot water use. We don't know much about. This is a building for a normal single family, family with 2 children and 2 adults, and this is what it was accounted for. The electricity used for appliances and plug loads, those were also lower than the expected ones. And I will say that the expectations were set very low. So actually this family didn't use much in general. Only the production of the thermal system was as expected, as well as the PVs. Those are the systems we could count on. So, as now you were saying that once we are comparing those energy spendings, those have to be compared to the actual indoor air quality, the thermal comfort, the outdoor conditions, and so on. So that's where we started on the point 1, where we had our measured data. This is in the point 1. We are not going to distribute it to the different parts, but so we had to do the correction. So we have corrected for the outdoor weather in the point 2. Then we correct for the indoor temperature in the point 3. Then we correct for the domestic electricity use because it was lower than we expected. We do that. Correct for the air tightness because there were some measurements done, and so on and so on and so on. So finally, when we took all of these corrections, then actually the predicted energy use was fit with the measurements. So actually a lot of things that we had to correct for the occupant was finally corrected, and then we could actually get the goal. So if you look at those results, then actually user behavior was impacting the energy use of the building by 62%. And this is a thing that we have to think about, because we can continue improving our building performance, but occupants have quite a lot to say. These are the measurements of the operative temperature in the building within a year. And on the x-axis is the outdoor temperature. And what you can see here is that while the outdoor temperature was reasonably low, we had the variation within the comfort level. For some cases, actually, the temperature in the room was lower. With the high outdoor temperature, the temperature inside of the building was increasing. And if we plot those results in those pie charts, you can see that for the first year, the comfortable environment of the building was experienced for 59% and 20%. For the next year, once we have learned more about the building performance, then actually the indoor thermal comfort was improved. So those are, with the green and orange, is the good performance of the building. And the second year, the year 1 and year 2 are with the people, with the family living in. And you can see once the people moved in, the indoor environment, thermal, had been reduced significantly. So the comfort period was much shorter. For the first year, once they have learned how to live in the building and deal with all of the systems, what we normally experience, in the year number 2, actually the comfort level of the building has been significantly improved. And this is improvements by the occupants of them learning how to live in this type of building. I must say for myself, I'm also living in a similar building, and the same as my neighbors. And all of them, they complained quite a lot for the first year because it's been very, very hot in their homes. After some time, they have learned how to deal with their homes, and now there are no complaints. It's all very well. So we are learning. So this is something that for consideration, that actually maybe it's not so easy for us to reach our goals by only improving the building core, or let's say building insulation and the air tightness of the building, but we have to deal with the occupants. It's been, but to the larger extent, because of the woman who lived here this year, she was on maternity leave. And you can see there are quite a lot of windows and no trees around, so anyone passing by could see her breastfeeding. So she had to shut the windows by curtains for longer periods. So that was one of the issues here. So the thing was to say here is that we are, besides having those very steady systems in our buildings, we actually have to work with the systems that are controlled. And that's the demand control, ventilation, that's shading control, lighting control, etc. And having those controls is a sensitive matter here, because they are not so steady and they influence building performance quite a lot. And this is what we have not been working on as much. And in this building is an example where it has been demonstrated that it is very sensitive to the control. And the user interaction had quite a lot to say for the final energy and the comfort performance. Yes, and I'm not going to spend quite a lot of time on the reflections. I think those are more or less the headlines of what we have been talking about. And those are available on the USB disk, so I can keep the time and stop here. And if you have any questions, you're welcome to ask me. If I cannot answer, I can provide you with the literature. So, thank you.